In a famous experiment, a neural network looked at a panda and was 58% sure. Researchers added a tiny layer of noise, invisible to your eyes, and the same network became 99% sure it was a gibbon. That's an adversarial example. Welcome to Episode 3. This is the attack that launched the field of AI security. Adversarial examples. Inputs that look completely normal to a human, but are carefully crafted to make a model confidently wrong. Here's the definition. An adversarial example is an input with a small, deliberate perturbation added to it. The change is so tiny that humans can't see it, but it pushes the input across the model's decision boundary, flipping the prediction. This is an evasion attack. It happens at inference time on the deployed model. Let's see it. On the left, a clean image the model labels panda with modest confidence. In the middle, an adversarial perturbation scaled up here, so you can see it, but in reality imperceptible. Add them together, and the model now screams gibbon with 99% confidence. Same picture to you and me. How is the noise crafted? With the model's own gradients. Normally, we compute the gradient of the loss with respect to the weights to train the model. Here, attackers compute the gradient with respect to the input and take a tiny step in the direction that increases the error. That's the fast gradient sign method, FGSM. Iterate it, and you get even stronger attacks like PGD. Why does this even work? Because neural networks carve up a very high-dimensional space with decision boundaries that sit surprisingly close to normal inputs. A small nudge in just the right direction crosses that boundary. And here's the scary part. The same perturbation often transfers, fooling models it was never even designed against. This isn't just a lab curiosity. A few stickers on a stop sign can make a self-driving car read it as a speed limit. Specially printed patterns can hide a person from a detector. Pattern glasses can fool face recognition. When AI controls the physical world, adversarial examples become a safety problem. So how do we fight back? The strongest known defense is adversarial training. You generate these attacks during training and teach the model to resist them. It's not perfect, and there's a cost in clean accuracy, but it's the gold standard. We'll cover the full defense toolkit later in the series. Adversarial examples attack the model after it's trained. But what if you could corrupt the model before it ever ships? That's data poisoning, and it's even more dangerous. That's Episode 4. Subscribe so you catch it. That's adversarial examples. A whisper of noise, computed from a model's own gradients, can make it confidently wrong, and that has real safety stakes. If you found this fascinating, hit like and subscribe. Next, poisoning AI at the source.